In this video, I'm going to go over the Unit 7 test, the multiple choice portion. There were 15 multiple choice questions on this assessment. Again, it's going to be closed if you have not taken this portion of it, but there is a retake available that you can do. So let's go over it. These are out of order from probably what you have, so just kind of find the question that you have and you can kind of see it being worked out. All right, so this question, which of the following has the smallest probability? So we can do this problem using the calculator. All right, so it says randomly selecting a value below 2 with t-distribution of 5 degrees of freedom. So we're going to go to second vars TCDF, which is 6. And if it's below 2, then we're going to have negative 1e99, and the upper is going to be 2, 5 degrees of freedom. And you get 0.949. All right, that's pretty high probability. That is your answer for that one. So let's write that out there, 0.949. And then just do the next one, randomly selecting a value above 2. So that's going to change the way you input it. You would do second vars TCDF. But this time you want 2 to be lower, and you want your upper to be infinity. This is going to be 10 degrees of freedom. So let's take a look at that. And that's pretty small, 0.0366. All right, randomly selecting a value above 2 from a t-distribution of 5 degrees of freedom. So above 2 is going to look like the last one, but we're going to change our degree of freedom. I'm just going to scroll up here and see if I can redo that. So we'll press delete, put in 5, and that's going to be a higher probability, about 0.05. So that's 0.05. So far it's 0.036. And we're only select a value above 1. So above 1 is going to see second vars TCDF. Above 1, that's going to be my lower is 1 with 5 degrees of freedom. So I'm going to change that to 5. And that's 0.18, so it's pretty high. And the last one, randomly selecting a value below 2. So one more time, we're going to second vars 6 below 2. We're going to start negative 1 E99. Go to 2 for your upper and 10 degrees of freedom. And again, pretty high number, 0.96. So question wants to know, which is the smallest probability? So that's just going to be this one here, above 2 with 10 degrees of freedom. All right, next question. All right, number 2, an experiment to test the effectiveness of regular treatments with fluoride varnish to reduce the tooth decay involved 36 volunteers who had half of their teeth, the right side or left side, determined by a coin flip, painted with a fluoride varnish every 6 months for 5 years. At the end of the treatments, the number of new cavities during the treatment period was compared on treatment fluoride varnish side versus the control no fluoride varnish side, the appropriate statistical test for analyzing the results of the experiment. Well, this is going to be a paired test. Anytime you have the same subject, there's going to be different treatments. That's a paired T. So same subject, different treatments, comparing one to the other. That's going to be a paired T. So I'll be that one there. All right, number 3. The water diet requires you to drink 2 cups of water every half hour from the time you get up until you go to bed, but otherwise allows you to eat whatever you like. 4 adult volunteers agreed to test the diet. They are weighed prior to beginning the diet and after 6 weeks on the diet. The weights in pounds are. So you have 4 volunteers. Notice that each person is doing the weight before and after, comparing them. So again, this is going to be in paired T. But this question is not really asking anything about paired T. It's asking what type of, what would a type 2 error be for this test of water diet. So again, a type 2 error is when you fail to, see that 2, 2 there, reject the null when it's false. All right, you fail to reject, which means you think the null is true, but it's not true, right? You should have rejected it. So what would failing to reject the null in this case look like? Well, that means failing to reject means that you are concluding, and I'm not reading the answer choices here, I'm just looking at it from my own perspective. You're concluding that the diet does not work. That's failing to reject the null. You're concluding the diet doesn't work when it does, because remember the null is no difference. So you're not rejecting that, so you're concluding it doesn't work when it does. So what does that correspond to over here? Conclude that the diet leads to weight loss when it doesn't. That's type 1. Draw a conclusion from this test when the normality condition has not been satisfied. Nope. Concluding that the diet leads to weight loss when it really does. That doesn't make any sense. And not concluding that the diet leads to weight loss when it really doesn't. And not concluding that the diet leads to weight loss when it does. That would be the best option. Concluding that the diet doesn't work would be not concluding the diet leads to weight loss. So that would be your type 2 error in this case. Not concluding the diet leads to weight loss, failing to reject when it does. All right, let's look at the next question here. The infamous psychologist, Dr. Weisskopf, claims that his secret sleep tapes cause people to become better at basic algebra. All you have to do, the doctor explains, is listen to my tapes while you sleep at night, and you'll be better at algebra in 2 months. A math teacher at a local high school has expressed interest but demands evidence. 5 people are randomly selected from students at the school. They take an algebra skills test, listen to Dr. Weisskopf's tape for 2 months while they sleep, and then take a second test. The test scores are as follows. Once again, this is going to be paired data. Paired data, because this is a before and after, right? So it's going to be a paired t-test. So which of the following conditions must be met in order to construct a 99% confidence interval? So paired t-interval, I guess, not test, for the true mean difference in pre-test and post-test scores. So when we're talking about the normality condition, all you got to worry about is the difference is approximately normal. You don't have to worry about the individual samples normal. You want to know the difference is approximately normal. Because all we're trying to take out the variability in this, right? We want to know, is that difference, is there any strong outliers or skewness to that? So the distribution of both pretest scores and post-test scores must be approximately. We don't want both, right? That's not, we don't need that. All 3, we don't need all 3. We don't need pretest, post-test, and the difference. We just need the difference. So only the distribution of the differences is approximately normal. The distribution of pretest scores and the distribution of the differences. Nope. Just the differences. And only the distribution of pretest scores. No, we need the differences. So only that when you're doing a paired t interval or test. That's the only condition for the normality. All right, question 5. Oh, I suppose we were testing the null hypothesis. Mu equals 50, and the alternative mu is not equals to 50 for an approximately normal population. A random sample of 9 observations are drawn from the population. The sample mean of these observations is 53 with a standard deviation of 6.48. Which of the following intervals contains the p-value for this test? What on earth? All right, so let's run this test for a minute. First of all, we have all the information, right? We have our, this is a one sample t-test, right? We got all the data to put in. We want to know what the p-value is. So we can go right into our calculator and put that in there. Second plus 712. Let me clear the memory for a second. All right, so let's go over here. We're going to go to test. We're going to go to t-test. We're going to go to stats. We're going to input our data. So our null, we said is 50. So put that in there. Our sample mean is 53. Our standard deviation is 6.48. And it said 9 observations, right? So that's going to be your n. So we can put 9 right in there. And this is not equals. So literally just, we got to plug and chug all that information right in there to get our p-value. So not equals, calculate, let's see what you get. We get 0.202, 0.202, which is above. 0.202 is above 0.2. So it's going to be this one here. All right, my number 6. An advertising firm is comparing 2 different 30-second television ads for a new mobile phone. A group of 48 volunteers is divided randomly into 2 groups of 24. And each group watches one of the ads. Afterwards, all the subjects are asked to estimate on a scale of 1 to 10 whether they would consider buying this phone the next time they upgrade to a new phone. So we want to let the mu1 and mu2 represent the mean rating we would observe for the entire population represented by the volunteers if all members of this population saw the first or second ad, respectively. Summary statistics are given in the table below. Dot plots for the 2 sets of ratings show no indication of non-normality. So basically, met all the conditions. The researcher tests the hypothesis. The difference is nothing versus the difference is not equal to 0. Notice that's not equal. All right, so it's two-sided. We got a p-value of 0.0045. Which of the following is a correct interpretation of this result? All right, so the way the p-values work is, if you look up interpretation of a p-value, interpret a p-value. So if the null hypothesis is true, there is a 0.0045 probability of getting a difference in sample means as far or farther from 0 as the difference in our samples. All right. Remember, a p-value is assuming the null is true. The probability of getting that sample or something more extreme than that is the p-value. That is textbook interpretation right there. Let's look at the other ones. The probability of the mean difference is equal to 0 is 0.0045. That is not true at all. If the null hypothesis is false, we have to assume it's true, so we can eliminate that. The probability of the test resulted in a type 2 error, nope, has nothing to do with that. If the tests were repeated many times, you'd make a type 1 error, no. Assuming the null is true, the probability of the p-value is the probability of getting that probability is of excuse me. The p-value is the probability of that number or something of that sample of getting that probability or something more extreme. That is the p-value. Sorry, I got kind of jumbled there in my words. All right, let's look at the next one. All right, the mean time it takes for a person to experience pain relief from aspirin is 25 minutes. A new ingredient is added to help speed up relief faster. Let mu mean the true mean time to obtain pain relief. Experiment is conducted to verify if the new product works more quickly. What are the null and alternative possible? Well, the null is always going to be equals, so we can get rid of these ones. But more quickly is a lower time, right? So we want the time to be less than 25 minutes in your alternative, not greater, because that would be slower. We don't want to be not equal because that would be slower or faster. This is quicker. Less than 25. All right, number 8. An agricultural researcher plants 25 plots with the new variety of corn. 90% confidence interval for the average yield for these plots is found to be 162.72 plus or minus 4.47 bushels per acre. Which of the following will produce a confidence interval with a smaller margin of error than this one? All right, smaller margin of error can be gotten a couple different ways. First, we can either, if we want a smaller margin of error, we can decrease the confidence level. We can do that. Lower confidence level, smaller margin of error. That's one way. You can also increase the sample size. So those two things will make the margin of error smaller. Well, we started with a 90% confidence level. Going up to 95 is going to make that larger. So that's no good. Reducing the bias, unfortunately, that doesn't really have anything to do with the margin of error. None of these is not an option. Planting 100 plots rather than 25, this is n got bigger. That's going to make your margin of error smaller. That's a good thing. Or using 25 control plots from an old variety cord. That's not going to do anything. But we've increased our sample size. So since we've done that, we're going to have a smaller margin of error. All right, number 9. We wish to see the dial indicating the oven temperature for a certain model oven is properly calibrated. 4 ovens of this model are selected at random. The dial on each set is 300 degrees Fahrenheit. And after 1 hour, the actual temperature of each is measured. The temperatures measured are 305 degrees, 310, 300, and 305. Assuming the actual temperature for this model when the dial set is 300 are normally distributed with the mean mu, we test whether or not the dial is properly calibrating, testing the hypothesis that the null is 300 and the alternative is not equal. What is the test statistic for a one sample t-test? Well, we could run the test, but the formula for the test statistic is always going to be your average minus your null. Remember, this is your null over the standard error. So first of all, what is the standard error? If we look on your formula sheet, standard error for one sample is always going to be the standard deviation over the square root of n, right? Now, are we given the standard deviation? No. However, if you look at your answer choices here, just use a little bit of common sense here. That is always 4.08, right? So that's going to be your standard deviation. Now, if you run the test here, you'll get that standard deviation as 4.08, or if you just put your numbers in your stat menu. So we can do that if we want to, but I'm not going to. But it's the standard deviation over the square root of n, so we can get rid of that. And what is n? Well, we have 4 different temperatures. N is going to be 4. So we want 4 to be under the square root symbol, not 3. So now we're stuck with these two, right? Well, what is your null? Your null is 300, right? That's going to be here. So 300 is what's subtracted. So we got 4.08 divided by the square root of 4. Well, what's going to be over here? Well, this must be your sample mean, 305 degrees. So just kind of based off of that alone, it's going to have to be this one here. It's going to have to be 305 minus 300 over 4.08 divided by the square root of 4. Now I can tell you, we can get that information. Here, let me clear this out for a second here. Write that down if you need to, or take a picture. All right, if you didn't remember the formula, you could go through and let's see, go to your stat menu here, and you could enter those 4 values in. All right, so we have our 4 temperatures. We could run the t-test. So stat tests. This is just the one sample t-test. We put our our null hypothesis at 300. Oh, let's go to data. So we put our null hypothesis at 300. Use L1 for your list, and this is a not equal, and calculate it, right? So you get that, there's your 4.0, there's your standard deviation. Well, this is your t, 2.449. Now, if you go through 2.449, write that down, and you go over here and you test, well, which one of those is going to give me 2.449? Well, it's going to be this one right here. All right, go through and actually calculate that. 305 minus 300, that's 5. And then divide that by 4.08 divided by the square root of 4. There's your 2.45 right there. That's your t. So there's your information right there. All right, number 10. Some researchers have conjectured that stem splitting disease in peach tree seedlings might be controlled with weed and soil treatment. An experiment was conducted to compare peach tree seedling growth with soil and weeds treated with one of 2 herbicides. In a field containing 20 seedlings, 10 were randomly selected from throughout the field and assigned to receive herbicide A. The remaining 10 seedlings were to receive herbicide B. Soil and weeds for each seedling were treated with the appropriate herbicide at the end of the study period. And at the end of the study period, the height in centimeters was recorded for each seedling. A box plot of each data set showed no indication of non-normality. So basically the conditions were met. So what would be the confidence interval? Basically, we'll go through this as we have 2 different means, right? This is a confidence interval, the difference in 2 means. And let's go through, hold on, let me find my formula sheet here and we'll, I had to pull this up here just so I could show you on the formula sheet. You'll notice that standard error, which is what we want to look for here, that's going to be n, not n minus 1. So kind of off the bat here, we're splitting this 20 up into 2 samples of 10, right? So your n's are going to be 10. We can go through there and we can eliminate the ones with 9s, right? Because we don't want that. We want the ones with the 10s. So let's get rid of the 9s. Now let's look at these 3 here. This one here doesn't even have a T star, right? So that's problematic, right? We have to have a number in front of those because it's the difference in the means plus or minus the critical value times the standard error. Well, we don't have the critical value here, so we can get rid of that. So now we can narrow it down to these 2. And they're identical except for this number, right? So the question says, how do you get determine your T star? Well, I like to use inverse T. It says use a conservative degree of freedom. So it's going to be the lesser of the sample size. So your degree of freedom, since your sample size were both to 10, and 1 is 10 and 2 is 10, your degree of freedom is going to be 9. Well, how do we get that? Well, this is going to be, what was it, a 95%? So first thing we want to do is we want to look into, I like to do inverse T, second bars, 4. And I want to average that 95% with 1. So it means I'm going to add that to 1 and divide by 2. That's going to be at 97.5%. And degree of freedom is going to be n minus 1, so 9. So your critical value is 2.26. 2.262. So it's going to be the 2.262 that you see here, right? That's the number we're going to use. So that's going to be your answer. So another critical value question. So I can keep this up here. Number 11, what's the critical value T for 90% confidence interval was n is 15? Well, again, go through it. Inverse T, we're going to change that 0.95 to 90. And the degree of freedom will be 14. And we'll paste it. And that's just calculator work right there, 1.761. So 1.761 is going to be this one right here. Okay, number 12. An SRS of 100 postal employees found that the average time these employees had worked for the Postal Service was 7 years with a standard deviation of 2. So the distribution of the time population employees has worked for the Postal Service is approximately normal. Which of the following gives the correct 95% confidence interval for the mean time of the population for Postal Service employees have worked for the Postal Service? So this is a confidence interval, a T interval. One sample, pretty basic. 7 is your average, N is 100, X bar is 7, S of X is 2. We can just we can work this out right into the T interval. It's going to be number 8. And go over to stats, and let's see. So our X bar is going to be 7, standard deviation of 2, and our N is going to be 100. At confidence level 95%. So you just kind of input it like that. And you get your interval about 6.6 to 7.4. So 6.6 to 7.4. Which one does that correspond to? Well, if you're going between 6.6 and 7.4, your mean is going to be 7. So you're going 0.4 in either direction. So your margin of error is 0.4. That's going to be that one right there. 7 plus or minus 0.4. All right, number 13, the infamous psychologist Dr. Weisskopf claims that his secret sleep tapes cause people to become better at basic algebra. All you have to do, the doctor explains, is listen to my tapes, you sleep at night, and you'll be better at algebra in 2 months. A math teacher at a local high school has expressed interest but demands evidence. 5 students from the school are randomly selected. Take an algebra skills test, listen to Dr. Weisskopf's tape for 2 months while they sleep, and then take a second test. The test scores are given here. Which of the following is the correct 99% confidence interval for the true mean difference? Post-test minus pre-test in scores. Mean difference. This is a paired test. Really? So it's going to be one sample. And that sample is the difference. So we can eliminate that 2 sample one right there. And so that difference here, well, it's going to be 1.2. So we got to figure out what's the correct, first of all, we don't know the T star here. So which one is the right T star? But then we can eliminate here because remember, this is going to be N. There's 5. So we don't want to do the one with 4, right? We can get rid of that. So we've got to narrow down to this. And just looking at that 5 there and that 5 there, really it amounts to what is that T star? So we can get that using inverse T. Second var is 4. And this is a 99%. So we're going to go ahead and go to 0.99. Average that with 1, and the degree of freedom will be 4. Because remember, the degree of freedom is 1 n minus 1. So, and then the T star, that area is the average with 1. So let's go ahead and get that here. And there's your T critical value, 4.6. So it is going to be this one here, not that one or that one. So it'll be that one. All right, next question. Blower dot plots from 5 different samples. Which sample does not satisfy the large sample normal conditions for performing one sample T procedures? Well, we have 5 different sample sizes. And I don't care what the distribution looks like. If you got a sample size greater than 30, see how these are skewed? But it doesn't matter, right? This one's skewed, but it's fine. Large enough samples means you're gonna meet that normal condition. This one has 32, it's evenly distributed, so it's not a big deal, but either way, it's bigger than 30. Our issues come with these 3. Which one of those, since they're all under 30, we have to find the one that has outliers or skewness or abnormalities. This one's pretty good, right? That's no strong skew. This one's pretty evenly distributed, but this one has an outlier. And even though it has 27, it didn't meet that 30 threshold. That's less than 30. And so we need to make sure we don't have any outliers or strong skewness for that normal condition to be met. So that's going to be the one that does not meet the requirements here, C. So in this case here, sample C would be your answer. And our last question, 2 independent random samples of size 50 and 75 are drawn from populations 1 and population 2 respectively. In order for T procedures to be valid, what must the size of each population be? This is the 10% rule. You don't want to be sampling more than 10% of your population. So if you take that and times by 10, and times by 10, we want our samples to be at least that much. So 50 times 10 is 500. And 75 times 10 is 750. You want N to be at least, both samples N1 and N2 to be at least greater than 500 and 750 to meet that 10% rule where you're not sampling more than 10% of your population. So it's going to be this one here. So let's go ahead and submit that. And again, this will not be counted for you, but you can do the retest. It'll be very similar questions. But as you can see here, I missed one here. Which one did I miss? Go over that real quick. Oh, I picked the wrong one. Dang it. We had picked the one that had the this one right here. It should have been the 2.262. I don't know why I clicked on that one, but that one should have been our answer here for that. But yeah, everything's good. You can go through there and check them on your own. Just try it as a practice and do the retest for the actual test grade.